Hello everyone, welcome to a new topic of chemistry called electrolysis. First, we will examine the difference between electrolytes versus non-electrolytes. Electrolyte is a substance that is either molten or dissolved and can conduct electricity, hence it can participate in electrolysis. Non-electrolytes cannot conduct electricity under any circumstances and hence cannot participate in electrolysis. Next, we examine the electrolytic cell. The electrolytic cell is simply the apparatus in which electrolysis takes place. Then, we examine the electrolysis of molten compounds. Molten compounds are easy to analyze because there is only one positive ion and one negative ion. Next, we analyze the electrolysis of aqueous solutions. This is more difficult because of the presence of 4 ions altogether. Next, we talk about the factors affecting electrolysis. This is the most difficult part of the topic. Depending on the situation, depending on the electrodes, depending on the ions present, different ions can be discharged. Next, we talk about the purification of metals using electrolysis, electroplating of objects using electrolysis, and finally, we examine the simple photovoltaic cell. Let's examine the difference between electrolytes and non-electrolytes. An electrolyte is a substance that can conduct electricity when molten or when dissolved in water to form an aqueous solution. A non-electrolyte, on the other hand, cannot conduct electricity under any circumstance. Electrolytes usually refer to ionic compounds because ionic compounds contain ions which have the potential to conduct electricity, but only when they are molten or when they are dissolved in water. The act of melting or of dissolving the ionic compound is to free the ions so that they are free to move and free to flow with the electricity. Examples of ionic compounds that can form electrolytes are therefore molten lead bromide or copper sulfate solution. In the case of the lead bromide, when it is molten, the Pb2 plus ion and the Br minus ions are separated from each other and are free to move and free to conduct electricity. In the case of the copper sulfate solution, the water is able to separate the copper 2 plus ions from the sulfate ions, and hence these ions are free to move and free to conduct electricity. At the same time, the water also introduces H plus ions and OH minus ions. Finally, we look at non-electrolytes. Non-electrolytes are usually covalent compounds because covalent compounds have absolutely no ions, so they will not be able to conduct electricity under any circumstances. Thank you. Hi, let's talk about the electrolytic cell. The electrolytic cell is the apparatus which performs electrolysis. It comprises of a battery, which is the energy source that drives the current through the cell, the electrolyte that's being electrolyzed, and 2 electrodes that electrically connect the electrolyte to the battery source. There are 2 electrodes, the anode as well as the cathode. Now the anode attracts anions. Since anions are negative ions, the anode is a positive electrode connected to the positive end of the battery. Similarly, the cathode attracts cations. Since cations are positive ions, therefore the cathode must be a negative electrode since opposites attract, and hence the cathode is also connected to the negative end of the battery. Officially, the anode is referred to as the electrode in which oxidation takes place. Now, if you would remember, oxidation involves the increase of the charge of the ion. As an example, let's examine the electrolysis of sodium chloride. Now, in the sodium chloride, the chloride ion is the negative ion, it is the anion. During the electrolysis, it will return to its original state as a chlorine molecule. And doing so, it will give up 2 electrons. So 2 electrons will be given up to the battery. Now notice the chloride charge increases from -1 to 0. Hence, it is an oxidation. On the other side, we have the cathode, and that is defined as where the reduction takes place. So in this example, the sodium ion is going to be discharged as the sodium atom, and that involves the addition of an electron to become the sodium atom. Since the sodium ion decreased in charge from +1 to 0, hence this is a reduction. Let's examine the electrolysis of molten sodium chloride. In the electrolyte, there are only 2 ions, the negative chloride ions and the positive sodium ions. The negative chloride anion is attracted to the positive anode, while the positive sodium cation is attracted to the negative cathode. At the anode, the negative chloride ion will give up electrons and return to its natural chlorine molecule state. So the electron will flow from the anode towards the battery. On the other side, we have the positive sodium ions receiving the electrons and returning back to its original sodium metal state. This is the cathode. So the electrons are pumped out by the battery from the negative end of the battery to the cathode so that it can be combined with the sodium ions to become sodium atom. Notice that at the anode, the chloride ion increases in charge from -1 to 0, and that is an oxidation. So oxidation happens at the anode. In the case of the cathode, we have the sodium ion decreasing in charge from +1 to 0, and since this is a reduction takes place at the cathode. Hi, let us now analyze the electrolysis of aqueous copper sulfate solution. Now, in that solution, there are 2 cations and 2 anions. The copper sulfate itself will produce the copper 2 plus ions as well as the sulfate ions. Water will provide the hydrogen ion and the hydroxide ion. In this case, both cations, the copper 2 plus as well as the hydrogen plus, will be attracted to the negative cathode. On the other hand, the negatively charged anions, the sulfate ion and the hydroxide ions, will be attracted to the positive anode. So now we have to decide which ion will get discharged. In the case of the anion, the reasoning is simple. Whenever you encounter sulfate ions or nitrate ions, they are never discharged. Between the hydroxide ion and the chloride ion, the discharge depends on the concentration. In a concentrated solution, the chloride ion will be discharged. In a dilute solution of a chloride solution, the hydroxide ion will be discharged. But in any case, in our example here, there are no chloride ions, there are no nitrate ions, and since sulfate is never discharged, obviously hydroxide ions will be discharged. How do we write out the equation for the discharge of the hydroxide ion? First, we must know the products of hydroxide ion discharged. Fundamentally, it is the oxygen gas. Right? Oxygen is in the electronic state or the oxidation state of -2. And from -2 state to 0 state, that's an increase of +2. That is an oxidation. That's why this happens at the anode. However, we need to include some compound to account for the hydrogen here. So we add water, H2O. Okay, now let's balance the equation. We've got 2 hydrogen on the right hand side. We need to have 2 hydrogen on the left hand side. Now notice we have 2 oxygens on the left hand side, but now we have 3 oxygens on the right hand side. But if we put a half here, then we have half times 2 is 1 oxygen plus another oxygen, that will be 2 oxygen. Now it is balanced. However, we do not ever accept fractions as equations. Hence, we need to multiply it throughout by 2, which becomes 4 hydroxide, gives you oxygen plus 2 water. Now, it's not just the atoms that must be balanced, the charges must also be balanced. So the left hand side, there are 4 negative charges, so the right hand side, we must have 4 negative charges, exactly as you see right here. Don't forget to include the state symbols. Hydroxide is in aqueous state, water is in liquid state, and gas, oxygen, is in gaseous state. Next, we have to analyze the discharge, the preferential discharge between copper 2 plus and hydrogen ion. To do that, we need to refer to the reactivity series. The reactivity series is potassium followed by sodium, followed by calcium, followed by magnesium, followed by aluminium, followed by zinc, followed by iron, followed by lead, followed by copper, silver, and gold. So these are the metals, but in between iron and lead we have, or rather in between lead and copper we have the hydrogen ion. Now as you go up the reactivity series, the metal becomes more reactive. If it's more reactive, it would prefer to stay in the reacted state, in the ion state. Conversely, if we go down the reactivity series, then the ion would become less reactive, so it would be more acceptable to return to its original metal state or original element state. Now between the hydrogen ion and the copper ion is lower down in the reactivity series, so copper is less reactive than hydrogen, so it will be preferentially discharged. It will prefer to return to its element form, so that's why the copper is the one that's being discharged. And in this case, the copper ion will receive 2 electrons from the battery and return back to its element state. Hi, let's talk about the preferential discharge of cations. First, we must remember very clearly the reactivity series. The reactivity series starts with the potassium ion, followed by the sodium ion, followed by the calcium ion, followed by the magnesium ion, followed by the aluminium ion, followed by the zinc ion, followed by the iron ion, followed by the lead ion, followed by the hydrogen ion, followed by the copper ion, followed by the silver ion, and finally the gold ion. As we go up the reactivity series, the cation becomes, or rather the metal becomes more reactive. When the metal becomes more reactive, it would prefer to stay reacted. And because it prefers to stay reacted, it prefers to stay as an ion. And because it prefers to stay as an ion, it tends not to be discharged back into its element form. Now on the other hand, when we go down the reactivity series, we find that the metal or the element becomes less reactive. Because it is less reactive, it has less tendency to stay in the ion form. Because of that, it has greater tendency to be discharged back into the element form. In other words, when comparing cations, the cation that is lower in the reactivity series will be discharged. For example, if we have an aqueous solution of copper 2+, we are comparing hydrogen ion and copper ion. In this case, the copper ion will be discharged. However, if we were to have an aqueous solution of magnesium ions, then we are comparing the magnesium with the hydrogen ion, in which case the hydrogen ion will be discharged and the magnesium ion will not be discharged. Hi, let us now look at the preferential discharge of anions. Sulfate anions will never get discharged. Nitrate anions will never get discharged. So we only have to concern ourselves with the hydroxide ions on the one hand and the halide ions on the other hand. Halide ions meaning ions made from group 7 halogens. Halides like the fluorides, the chlorides, the bromides, and the iodides. Now, whether the halides are being discharged or the hydroxide ion is being discharged depends on the concentration. When the solution is highly concentrated in the halide, be it the fluoride or the chloride or the bromide or the iodide, then the halide will be discharged. In the concentrated solution of the halide will be discharged. However, when the solution is dilute, so in a dilute solution of fluoride or chloride or bromide or iodide, then the hydroxide ion will be discharged. So in a dilute solution of the halide ion, the hydroxide ion will be preferentially discharged. Hi, we will now look at how the electrodes themselves affect the outcome of electrolysis. There are two types of electrodes. One, the inert electrodes. The inert electrodes are unreactive, they will not participate in the electrolysis. Examples of inert electrodes are graphite or carbon electrodes and platinum electrodes. These are inert, they are unreactive, they will not partake in the electrolysis. Now, copper is a reactive electrode, particularly if the copper electrode is the anode, then something else will happen. If the copper is at the cathode, then nothing will happen. Something will happen only when you use copper as the anode. First, we must understand what the battery is doing. The battery is drawing electrons from the anode and pumping them to the cathode. Usually, the source of electron comes from the anion, either the chloride ion, for example, or the hydroxide ion. The anion is rich in electrons, so the electrons can be stripped from the chloride or the hydroxide ion and be used to feed the battery and feed the cathode. However, if you were to use copper as the electrode, or rather if you use copper as the anode, then something else can happen, because copper can react. Copper can be oxidized, and when copper gets oxidized into copper ion, electrons will be released. In this case, the copper will gradually get dissolved into the solution. The copper anode will get smaller and smaller, and you will find the solution becoming more and more blue as more copper ions enter the solution. Hi, let's now talk about electroplating of metals. We can electroplate metallic objects with silver, which is silver plating, or we can electroplate objects with gold, and that's gold plating. Here we talk about the electroplating of objects with copper. The object to be electroplated will be placed at the cathode. So the object at the cathode is connected to the negative end of the battery. Pure copper is connected to the anode, to the positive end of the battery. During the electrolysis, the battery will draw electrons from the anode and push it out to the cathode. As the battery sucks electrons from the copper atoms releases the electrons and becomes copper ions. So they will appear to dissolve into the solution and cause the solution to turn bluer. However, that doesn't happen. Why? Because at the other end, you find that the electrons reaching the cathode will return the copper ions on the other side back to metallic copper. So the copper ions here receive the incoming electrons and return back to copper atoms. And these copper atoms stick to the cup and cause the cup to be coated with a layer of copper. As copper is being pumped into solution on the anode side, but removed from solution at the cathode side, overall there is no change in the concentration of copper in the solution. As a result, the copper solution's blueness remains unchanged. Hi, let us now talk about the purification of copper. Suppose you have a piece of impure copper. So there are impurities mixed with the copper. Now how are you going to purify that piece of impure copper? You attach it to the positive end of the battery so that this impure piece of copper becomes the anode. On the other side, on the negative side of the battery, you connect a piece of pure copper. So this piece of pure copper becomes the cathode. What the battery does is that it sucks electrons from the anode and pumps it to the cathode. As electrons are being sucked from the impure copper, the copper will go into solution to form copper ions and release the electrons. So the copper will go into solution as copper ions. As it does so, the impurities will drop from the to the bottom of the electrolytic cell. The copper ion in solution, because they are positive ions, they will be attracted to the negative cathode. And as they reach the cathode, they will receive those electrons and return back to element form. So the copper ions at the cathode will receive the electrons and return back to metallic copper atom state. In this way, the impure copper will get smaller and smaller as the copper dissolves and the impurities drop off, and the piece of pure copper will grow bigger and bigger and get coated with even more pure copper. At the end of the day, the anode will become empty and the cathode will be a big piece of pure copper. Let us now look at the simple voltaic cell, which is a simple battery. The simplest battery is just two different metals of different reactivities connected by an external circuit. In this case, zinc is more reactive than copper, so zinc will give electrons to the copper. As the zinc gives the electrons away, it will dissolve into the solution to become zinc ions. So when the zinc metal is completely dissolved, the battery will run out. On the other side, the electrons will be received by cations, and in this case, between the copper 2 plus ions and the hydrogen ions, copper 2 plus will be preferentially discharged because it is lower down the reactivity series. So the copper 2 plus will receive those two electrons and return back to copper state. Now let us identify the anodes and the cathodes. The definition of anode is the electrode where oxidation takes place. Now the zinc goes from 0 state to +2 state, so that's an oxidation. So the zinc electrode is the anode. On the other hand, the copper ion goes from 2 plus to 0 charge, or rather oxidation state. So this is a reduction, hence by definition this happens at the cathode. Hence this is the cathode. Now the direction of current flow is opposite to the direction of electron flow. Since electron flows clockwise, then current must necessarily flow anti-clockwise. But current flows from the positive end of battery to the negative end of battery. Now this whole gadget cell, this whole cell here is a battery, and the battery supplies current from the positive terminal to the negative terminal. Hence, this is the positive terminal, this is the negative terminal. Now notice now the polarities are now reversed compared to the electrolytic cell. In the voltaic cell, the cathode is positive, whereas the anode is negative. This is opposite to the electrolytic cell. In this second example, we look at another simple voltaic cell made up of two different metals. Since magnesium is more reactive than copper, magnesium will give the electrons to the copper, and in doing so, the magnesium atoms will dissolve into solution to become magnesium ions, providing two electrons. So as the battery is being used, the magnesium ribbon will get smaller and smaller until it's eventually totally dissolved. Then the cell will run out. On the other side, the electrons will be received by the cations. There are two cations, the sodium cation and the hydrogen cation. Again, for cation discharge, the one that's lower down the reactivity series will be preferentially discharged. In this case, the hydrogen ion will be preferentially discharged. The hydrogen ion will receive the electrons and return back to its element form, hydrogen gas. Because magnesium increase in oxidation state from 0 to +2, that's an oxidation, so the magnesium side is the anode. on the copper side, we have hydrogen going from +1 state to 0 state. That's a reduction in state, hence this is a cathode by definition. So again, we have anode here and cathode here. Similarly, direction of current flow is always opposite to direction of electron flow. So since electron flows clockwise, current flows anti-clockwise, and since current flows from the positive end of the battery to the negative end of the battery, now we have cathode being positive, anode being negative. Again, the polarities of the anode and cathode in a simple voltaic cell has been shown to be always opposite to that polarity in the electrolytic cell.